Welcome to the deep dive. Today we're zeroing in on a really critical skill, especially if you're aiming for a senior software engineer role.
Yeah.
Navigating the tricky landscape of changes between microservices. We'll be unpacking how to evolve these independent services without causing, chaos in your overall system.
Exactly. Think of it as mastering the art of keeping a complex network of interconnected parts functioning smoothly as each part evolves. The big question we'll be tackling is, how do you manage those inevitable changes to a microservice without breaking the integrations that already exist? And yeah, this goes beyond just sticking a version number on it.
Right.
It's really about building resilient and adaptable systems. Our goal today is to equip you with practical strategies you can not only implement, but also confidently discuss in, say, a technical interview setting.
Okay, so let's dive right in. When we're talking about preventing these integration headaches, what are some of the first principles we should be thinking about? Like, where do we start?
Well, a foundational idea is to prioritize adding to existing systems rather than taking away or modifying things in a breaking way. We often call this expansion
Look at
changes.
expansion changes. Okay.
Yeah, the core concept is that when a microservice needs to evolve, you should really aim to introduce new functionality without removing or altering existing capabilities in a manner that would disrupt current consumers.
That makes sense intuitively. Can you walk us through maybe a real-world example of how this might play out?
Sure. Imagine a service that holds customer information. Initially, it might just contain details like customer first name, last name, and email address. Pretty basic stuff.
Okay.
Now, let's say the business needs to start tracking, I don't know, a customer's marketing preferences. Instead of messing with the existing structure, the service could simply add a new field, maybe marketing opt-in.
Ah, okay.
Clients that were only interested in those original 4 fields would simply ignore this new addition and continue to function without any issues. The key is that they aren't expecting this new field, so its presence doesn't break them.
So this idea of gracefully handling extra information leads us nicely to the tolerant reader pattern. What's the core of that concept?
The tolerant reader is all about how you design the clients, the consumers of microservices. The aim is to make them as flexible as possible in what they accept from a service. Let's go back to our email sending service example.
Okay.
It needs customer data specifically, first name, last name, and email address to send out personalized emails. Initially, the customer data might be structured with customer, first name, last name, email address, and maybe even an unused field that someone added once.
Right. So the email service has a specific need for certain pieces of customer data. It doesn't care about everything, just those key fields.
Exactly. Now, if the team managing the customer data service decides quite reasonably to remove that unused field because nobody is actually using it, a client in this case, our email service that was built with the strict expectation that all 5 of those fields must be present could suddenly break.
Ouch. Yeah, I can see that.
Similarly, consider a scenario where the customer data gets reorganized. Maybe first name and last name are now nested under a personal info object. The essential data the email service needs is still there, but the structure has changed slightly.
Okay. I see the potential pitfalls of clients being too rigid in their expectations. So how does the tolerant reader approach actually mitigate these risks?
Well, a tolerant reader is designed to only extract the specific data it needs and to gracefully ignore anything else. So instead of trying to map the entire customer object to some predefined rigid structure, the email service could use a mechanism like, say, XPath for XML or maybe JSONPath for JSON
Okay.
to specifically locate and retrieve just the first name, last name, and email address, regardless of minor structural variations, as long as those fields are still present somewhere in the response.
So it's like having very specific instructions for finding exactly what you need in a document, even if the document's layout changes a bit.
Exactly. It makes the client more resilient to those minor, non-breaking changes in the service's response format.
That reminds me of Postel's law. Be conservative in what you do, be liberal in what you accept from others. It sounds like that principle is really at play here.
Absolutely. That's the fundamental idea behind the tolerant reader. In the microservices context, it means your client-side code should be written to anticipate and tolerate small, non-essential changes in the data it receives. It should be robust enough to handle extra fields or slightly different structures without failing, provided the core info it needs is still available.
Makes sense. Now, beyond how we design our clients, does the underlying technology we choose for our microservices themselves have an impact? Like, does it make it easier or harder to evolve them in a backward compatible way?
Oh, definitely. The right technology, or maybe the wrong one, can make a significant difference in managing interface evolution. Some technologies inherently create tighter couplings and can be, well, more brittle when changes occur.
Brittle, yeah, like what?
We could think back to older technologies, maybe things like Java RMI, that had very strict requirements about matching interfaces precisely between services. That often led to more headaches during updates.
Right, I remember those days.
On the other hand, certain modern technologies are actually designed with evolution in mind. They make it easier.
Can you give us some concrete examples of technologies that are more evolution friendly?
Sure. Protocol buffers, often used with gRPC, are a good example. They use this concept of field numbers. Each field in your data structure gets a unique number.
Uh-huh.
When you add new fields, you give them new numbers. Existing clients compiled against an older version of the definition will simply ignore the new fields because they don't recognize their numbers. It's sort of built-in backward compatibility for adding fields.
Okay, that's clever.
Avro takes a different approach. It often includes the schema of the data along with the data itself. This allows clients to dynamically interpret the data based on the schema they receive, offering flexibility even if that schema has undergone minor changes.
And what about when we're building, standard RESTful APIs? How do these principles apply there?
Well, REST has also seen advancements. HATEOAS, or hypermedia as the engine of application state, is an interesting, though sometimes complex, example.
HATEOAS, right?
The idea there is that the API's responses include links that guide the client through available actions. If the API evolves, as long as the client follows these links, it should theoretically adapt. But, implementing HATEOAS fully requires a pretty significant shift in how clients are built. It's a whole mindset.
Yeah, it's not trivial.
No. More practically, specifications like OpenAPI and JSON schema are becoming increasingly popular for REST APIs. These let you define explicit structures for your API requests and responses.
Oh, okay.
And that, in turn, makes it much easier to understand what can and cannot be changed without breaking consumers. It gives you that clarity.
This all seems to point towards the importance of having clear contracts between our microservices. You mentioned the idea of an explicit interface. Why is that so valuable?
Yeah, exposing a well-defined schema for your microservices endpoints, clearly outlining what each endpoint does and the structure of the data it exchanges is incredibly beneficial. For teams consuming your service, it provides a clear understanding of what to expect.
Right.
They know the format of requests they need to send, the structure of responses they'll get.
Makes their job easier.
Definitely. But it's equally crucial for the teams maintaining the microservice. A formal schema acts as a contract. It makes it much easier to understand which parts of the service are public and therefore need to be treated with extra care to avoid breaking existing clients. It really helps define the boundaries and manage those dependencies.
So with technologies like gRPC, having a schema defined using something like protocol buffers is just inherent to how they work, right? It's part of the deal.
Exactly. Many RPC-style communication frameworks rely on an interface definition language, or IDL, to specify the contract. That IDL is the explicit schema. REST, on the other hand, has historically been more flexible, often lacking that formal, machine-readable definition.
But that's changing.
Right. As we've discussed, tools like OpenAPI are really changing that landscape by providing a standardized way to define RESTful APIs.
Okay, what about when we're dealing with asynchronous communication, like using message queues or event streams? How do explicit interfaces play a role there?
That's an area that has definitely been maturing. While you can certainly define schemas for the message payloads themselves, and technologies like Avro are frequently used for this, establishing an explicit interface for event streams needs to go beyond just the data structure.
How so?
It needs to define what types of events a microservice publishes. What's the vocabulary of events? Fortunately, there's growing momentum here. Initiatives like AsyncAPI are trying to do for asynchronous APIs what OpenAPI did for REST.
Ah, interesting.
And then there's Cloud Events, which is a Cloud Native Computing Foundation CNCF project supported by services like Azure Event Grid. It's working to create standards for describing event data itself, including metadata about the event.
So standardization efforts are underway?
Yes, which will greatly improve interoperability and understanding in asynchronous systems. It's still, an evolving field, but the direction is positive.
Okay, so we're putting all these strategies in place: expansion changes, tolerant readers, good tech choices, explicit interfaces to avoid breaking changes. But let's be real, sometimes things still slip through. How do we catch those accidental breaking changes early before they hit production and impact users.
This is absolutely vital. You're right. Even with careful design, unintended consequences can pop up. That's where having robust mechanisms to catch accidental breaking changes early becomes essential. It's your safety net.
What kind of tools and practices are we talking about here? What does that look like?
Schema comparison tooling is a key element, especially if you are using explicit schemas like OpenAPI or protocol buffers. There are tools available. You mentioned Protolog for protocol buffers. There's JSON Schema Diff Validator for JSON Schema, OpenPDiff for OpenAPI specs. These tools can compare different versions of your schemas and highlight any structural modifications. But ideally, you want tools that go a step further and actually determine if those changes are backward compatible or not.
Like a pass-fail check.
Exactly, a pass-fail. Because that allows you to integrate these checks directly into your continuous integration CI pipeline. If a change is detected that could break existing consumers, boom, the build fails. It prevents the deployment of a potentially breaking change.
That sounds like a really effective safety measure. Are there any specific platforms or registries that help manage this kind of thing?
Yes, the Confluent Schema Registry is a notable example. It provides a central place to store and manage schemas for various formats: JSON schema, Avro, protocol buffers. Importantly, it can enforce backward compatibility rules when new schema versions are registered.
Oh, so it actively prevents incompatible schemas from being added.
Yes, you can configure it that way.
Yep.
While it originated within the Apache Kafka ecosystem, its utility really extends beyond Kafka. It can manage schemas for any type of data exchange.
But what if we're not using strict schemas across all our microservices? Or maybe the breakage isn't purely structural but semantic. How do we detect those kinds of breaking changes?
Yeah, that's a tougher challenge. In those cases, testing becomes even more critical. We're talking about approaches like contract testing and consumer-driven contracts, often abbreviated as CDCs.
Contract testing.
PACT is a widely used tool in this space. The fundamental idea is that the consumer of a service defines the interactions and data it expects from the provider. These expectations are then codified as test the contract. The service provider can then run these tests automatically to verify that they still meet those consumer requirements. This is particularly valuable when you don't have a formal schema, or like you said, when you want to catch those semantic breakages, changes in behavior or meaning that aren't necessarily reflected in the data structure itself.
So in essence, the consumers are helping to define and enforce the contract from their perspective.
Precisely. It's a collaborative approach. It helps ensure the provider doesn't unknowingly introduce changes that will negatively impact its consumers. Another important technique, by the way, is simply running integration tests using the actual client libraries your consumers use against the latest version of your service.
Right, testing it like a real client would.
Yeah, that can uncover issues that might not be apparent just from looking at the service's code or even its schema, of course.
Yeah.
Sometimes break-in changes are unavoidable. They just have to happen.
Yeah, business needs change.
Exactly. And in those scenarios, you absolutely need a well-thought-out plan for communicating these changes clearly to your consumers and ideally assisting them with the necessary updates. You can't just drop a breaking change on them.
Okay, all this focus on preventing and catching breaking changes is great. But how do we effectively communicate the nature and impact of changes to the teams consuming our services? That's where semantic versioning comes in, right?
Exactly. Semantic versioning, or SemVer, is a widely adopted convention. It uses that three-part version number, major.minor patch, specifically to convey the type of changes included in a new release.
Okay.
The goal is to give consumers a clear, immediate indication of the potential impact of upgrading just by looking at the version number. No digging through release notes initially.
So can you break down what each part of that version number signifies again? Major, minor, patch.
Sure. When the major version number is incremented, like going from 1.x.x to 2.0.0, it signifies that the release contains backward incompatible changes. Big warning sign.
Got it. Major means potential breakage.
Right. Consumers will likely need to make modifications to their code to integrate with this new major version. An increment in the minor version number, say 1.2.x to 1.3.0, indicates that new functionality has been added, but crucially, these changes are backward compatible.
So existing clients should be fine.
Generally, yes. Existing clients should continue to function without needing updates, though they might want to update to use the new features eventually. Finally, when the PCH version number increments like 1.2.0 to 1.2.1, it indicates that the release includes only backward compatible bug fixes to existing functionality.
Okay, so PCH should always be safe to apply.
That's the intention, yes. a safe upgrade.
Can you illustrate this with maybe that help desk example again?
Yeah, let's say our help desk application relies on version 1.2.0 of a customer profile service. If the customer profile service releases version 1.3.0, the team maintaining the help desk app can generally expect, okay, this adds new features, but our existing integration should still work.
Now, you also mentioned briefly the possibility of versioning entire services versus individual endpoints. When might you choose one approach over the other? Is there a rule of thumb?
Versioning an entire service is often the simpler and more common approach. It provides a clearer demarcation point for all changes within that service boundary. Everything moves together under one version number.
Simpler sounds good.
It usually is.
Right.
However, in more complex scenarios, maybe where you need to make a breaking change to a very specific isolated part of a service while keeping other parts stable and backward compatible for a longer time.
Ah, I see.
Then versioning individual endpoints, perhaps through URL path versioning like v1 resource and v2 resource, can offer more granular control. This can be useful for managing transitions, allowing consumers to migrate to the new functionality at their own pace. But
There was a but.
yeah, it definitely introduces additional complexity in managing the code, the deployment, and the routing of requests to the correct endpoint version. It's a trade-off.
Okay. It sounds like semantic versioning is a really powerful communication tool, even if maybe its universal adoption in complex distributed systems still has its challenges.
That's a fair assessment. It's incredibly valuable when used consistently.
Right. So to kind of summarize the key strategies we've hit on today, we've covered the importance of making expansion changes, adding, not subtracting, designing tolerant readers that are flexible, choosing the right underlying technology that supports evolution,
Yep.
defining those explicit interfaces or contracts, using schemas, implementing mechanisms to catch breaking changes early, things like schema validation and contract testing, and finally, using semantic versioning to effectively communicate the nature of those changes to consumers.
Precisely. And these aren't just abstract concepts you read about. They are practical techniques. They're crucial for building robust, maintainable, and truly evolvable microservices architectures. You need this stuff day to day.
Absolutely. And for anyone preparing for those senior-level technical interviews, being able to articulate these strategies, talk through the trade-offs, that really demonstrates a deep understanding of the challenges and best practices in designing and operating distributed systems. Shows you've thought about the hard parts.
Definitely. It separates, just knowing the buzzwords from actually understanding how to build things that last.
So as we wrap up this deep dive, here's maybe a final thought for you, our listeners, to consider. What are the long-term implications of really prioritizing strict interface contracts, very rigid schemas, versus maybe leaning more into the flexibility offered by tolerant readers? How might those different philosophical choices impact the speed of innovation versus the overall complexity of managing a large microservices ecosystem down the road?
Ooh, that's a good one.
Yeah, think about different real-world scenarios, maybe high compliance environments versus rapid growth startups, where one of these approaches might offer a significant advantage over the other. It's often not a black and white answer.
It rarely is. Lots of trade-offs.
Exactly. Something to chew on. Thanks for joining us on the Deep Dive.